All right, so last time we were working in section 3.6 and we're talking about curve sketching. In particular, there's several different features of graphs, some of them related to algebra things that we've done in the past, and some of them more related to the calculus things that we're doing now. In particular, finding where graphs are increasing and decreasing, have relative extrema, where they're concave and concave down, and where they have potential or actual inflection points. And so at this point in the problem, we had taken the derivative, and we had found out where it was increasing, it was decreasing, and we had drawn very little so far. We'd plotted a couple of points. We've also marked some asymptotes. Now, I mentioned last time as we were ending that there was a very strange thing that was happening here. So the dotted lines are the asymptotes, and there's a dotted line on both of my axes. The dotted line that feels a little bit odd is the one that's on the horizontal axis or the x-axis. Because not only is there a dotted line there, meaning it's an asymptote and we shouldn't be touching it, there's also an x-intercept there, which seems sort of counterintuitive. How do I have an asymptote and an x-intercept? So I sort of left you hanging last time. The reason that that's possible is because asymptotes really indicate end behavior. And so on the ends of this graph, I do have an asymptote along the x-axis. But I do have the ability in some cases to have the graph actually cross the x-axis even though there's an asymptote, and this one does. So it's not a mistake. We didn't do anything wrong or interpret something wrong. It's just one of those unique situations, and they don't come up all that often, but they are possible. All right, so the point where we are right now is taking a look at finding the second derivative and analyzing the concavity of the graph. I don't have a whole lot of space on this graph. I think, let me just flip to this screen right here. I'll turn it into a different background for now, and then I'll put it back into this background in a moment. Let's use, let's use a color backdrop. That's something lighter than that. All right. So we're going to take our second derivative. The first derivative that we have on the previous screen, I'll just rewrite it here for us again. The first derivative is, looks like negative 2x plus 12 over x to the fourth. Is that what you have? Okay. So we're going to take the second derivative now. And again, if you would like to do some algebra to simplify that and then take the derivative, you can. I'm just going to use the quotient rule this time instead, but both of them are viable options here. So the quotient rule says we take the denominator and then times the derivative of the numerator. So what's the derivative of this numerator? Thank you, negative 2 minus. And then I have my numerator, so negative 2x plus 12, and the derivative of the denominator, which is 4x cubed. And then I'll divide by the denominator squared, and that's going to give me x to the 8th. So we're going to clean up the numerator, distribute some pieces, simplify where they can combine. I have negative 2x to the 4th. And then I have, let's see, it looks like positive 8x to the 4th. And then negative 48x cubed over x to the 8th. And if I combine these two together, I'll have 6x to the 4th. So 6x to the 4th minus 48x cubed over x to the 8th. And I need to reduce. So how will that reduce?
6x minus 48.
Mm-hmm.
X.
Okay, that all good for everybody? So just with the first derivative, and just like you did on the quiz, in order to find inflection points in concavity, we set the second derivative equal to 0. So second derivative is equal to 0, and that really means, or to equal to does not exist, and it really means that either the numerator equals 0 or the denominator does, right? Where does this numerator equal 0? At 8. Where does the denominator equal 0? A typo in there. Yep. What was it? At 0. Yeah. And we already know what's happening at 0. I mean, it could change concavity there, but it can't be an inflection point there because there's an asymptote there. So I'm not going to get an inflection point there, but I could change concavity there. So we set up a sign chart. And we put those values in our sign chart. So I have 0 and I have 8. And I need to test values in each interval. So maybe we test -1, 1, and 10, something like that. And we're putting them into the derivative, right? The second derivative, the last one we just found. So if I evaluate this at -1, well, if I evaluate it at negative, the denominator is definitely negative, right? And then if I put a negative in beside the 6 and then subtract a negative, I'm going to get a negative on top. So we get negative divided by negative. The first one's positive. And feel free to just put it in your calculator too. If you don't want to reason through it, it's totally fine. The number 1 put in the bottom and the number 10, both of these are going to make the denominator positive. So whatever the numerator does is going to dominate here. So if I put a 1 in the numerator, I have 6 minus 48. That's going to give me a negative. And if I put a 10 in the numerator, 6 times 10 is 60 minus 48, I'm going to get a positive. So I do have an inflection point at 8. So there is an inflection point. At 8. 8 what? Well, we use our original function to figure out 8 what. So our original function was x minus 4 over x cubed. So if I want to find 8, I'm running out of space on this slide drastically. We're going to put it up here at the very top. I have, what is it? 8 minus 4 over 8 cubed. It's going to be very small. What is 8 cubed? 512. And then 4 divided by 512 is what? 1 over what? 128. Okay. And if you want in terms of actually looking at how we're going to plot this in a moment here as an approximation, it's about 0.008. That's the approximate value for plotting. The value that's actually the y value, though, is 1 over 128. So over here we have 1 over 128 for our inflection point. And we can also talk about where the graph is concave up and concave down. So it's concave up where? Mm-hmm. Right. So we're just reading it off of the sign chart. And then it's concave down in between those from 0 to 8. Okay, are all those details okay? Okay. So then, let me put my grid back on, and we'll have our graph. That's what I was using. So we're supposed to have a graph. Oh, I didn't actually. Let me put it over here too. Where did I write it? Oh, I wrote it out, but I didn't write it in details. So it was increasing from negative infinity to 0, increasing from 0 to 6, and decreasing from 6 to infinity. I'm going to write those down over here. So it's increasing from negative infinity to 0 and 0 to 6. And then it's decreasing from 6 to infinity. And I have a relative max. I already plotted it, but I had a relative max at, what was the value?
6, 1 over 100.
Like that. Okay. So this one's already plotted. So parts of these graphs overlap, right? Like this negative infinity to 0 is in both of these lists. I'm supposed to be increasing negative infinity to 0, and I'm supposed to be concave up. So I'm increasing and concave up on the left-hand side of the graph. So increasing and concave up, and I need to be trapped between the asymptotes. So I can't increase and be concave up down here, for example, because then I'd run into my asymptote, right? This is what increasing and concave up looks like, yeah? But I can't put it down here. So it must be over here like this. Remember, we're sketching. We're not plotting super specifics. We didn't have any points over there that we have to specifically go through. If you want to be a little bit more clear and you want to give a, just choose a random point, you're certainly welcome to. But this matches the descriptions that I have created so far, correct? It does. The next parts don't exactly overlap because this says it's supposed to be increasing from 0 to 6, and then this says it's supposed to be concave down from 0 to 8. So from 0 to 6, it's supposed to be increasing and concave down. Like both of those things are supposed to happen. So I need to be increasing from the y-axis until I get to 6, which is this little bitty tiny dot right there, and concave down. And it's okay that I'm crossing the x-axis because I have to hit that one point, right, at 4. So I am going to cross that point. It's going to look something like this. This is increasing and concave down. The part that's overlapping that's a little bit weird is that it's supposed to continue to be concave down all the way until I get to 8, right? But it's supposed to be decreasing from 6 on. So I'm going to be decreasing and concave down now. So that's going to look like sort of the decreasing part of a parabola, right? So it's going to be decreasing and concave down. And again, I'm not going to be able to plot this with any level of accuracy because the numbers are extremely small. But you can imagine I'm going to be hitting something right over here. It's slightly lower than it was before, and I'm supposed to be going downhill to get there. So I'm a little bit higher right now, and I'm going downhill to get there. And the next part is going to look even less helpful because it's such small numbers. It's okay. After 8, at 8, it's supposed to have an inflection point. Inflection point means it changes concavity. It's changing from a concave down graph, which it currently is, to a concave up graph. So it has to flip back around and be concave up now, right? But it has to do that from the end of the graph, so 8 to infinity. I think I was in the middle of a sentence. Sorry, it's not going to make any sense now, but that's all right. Okay, so I'm supposed to be decreasing, right? This one says I'm supposed to be decreasing after 6, and this part down here, 0 to 8, says I'm supposed to be concave up, right here, 8 to infinity. So increasing and concave up. It's not going to look real good, but it looks like this, and you can't even hardly see it. Let me actually do this and shift this down a little bit just so that I can draw something. Looks like that. So if it were exaggerated a bit, it would be doing this, like this. So it is changing concavity right here at that point, and then it flips to being concave up. That's the image if you were to sort of zoom in enough on a screen or something like that. It would look like that at that particular point. Does that help? Okay, the numbers on this one don't work out very nice, but that's the way problems sometimes happen, is the numbers don't work out nice. All right, let's do one more example. We're going to do the same thing as we did before. We're going to analyze and sketch this graph, but it's not a rational function like that has asymptotes and so forth. It's actually a radical function instead. So, there's one thing we didn't do. I mentioned that we would. I totally forgot. We left range blank here. Do you remember that? I told you we'd come back to it. If you take a look at this particular graph, the range is actually everything. All y values are accomplished because I actually do cross through that y equals 0 mark with an it was an asymptote, and it is an asymptote, but I also have an intercept there. So on my real, or my range, it's all real numbers. So either written like this, or you can go negative infinity to infinity if you prefer. Okay, back to the new one. All right, so we're running through all the list of the same things, domain and range. Domain and range on this one are actually pretty easy to do from the front end instead of from the back end, although you could wait if you wish. Range might be the easier of the two. The range means the output values. When I take a square root, like it's actually square root of something, the output is only going to be values that are positive, right? When a square root begins on a problem, it's actually called a principal square root, which means it's only the positive part of it. So I only get positive values, and I could get 0. So my range is actually from 0 to infinity, like that. Or you could say that y is greater than or equal to 0. That's my range for this one. Domain. Well, I've got a radical, a square root specifically. And underneath the square root, I can't have negatives. Can't have negatives, right? We're working with calculus in the real number system. No negatives underneath the radical. So the values that are here 2x minus 1 must be greater than or equal to 0, and I can solve that inequality. I can move my 1, so this is 2x is greater than or equal to 1, and divide by my 2, so x is greater than or equal to 1/2. Let me just try to keep this the same. So x is greater than or equal to 1/2, or if you wrote it in interval notation, it would be from 1/2 to infinity. Those are two different options of ways to write them. Is that okay for domain and range? Okay, that's not calculus. That's algebra stuff. Intercepts work very nicely as well. This graph has an intercept. In particular, you know that if x is equal to 1/2 right here, what does y equal? 0. That's one of my intercepts. So I get one of them for free because I've really already sort of gone through that looking at the domain and the range. So I have an intercept of x is 1/2 and y is 0. What if I try to let x equal 0? This is audience participation time. What if x is 0? I would get an imaginary output, right? I'd have a negative underneath the radical. I'm not inside my domain. All those things sort of fall apart. So there is no y-intercept. So this is an x-intercept. I didn't write it up there that way. Remember, your x-intercept is where y equals 0, and your y-intercept is where x is equal to 0. So there is no y-intercept. And the reason is because x can't be 0, right? I'm not dealing with functions that have asymptotes. This is not got a denominator. It's not in rational form. It's not a logarithm graph, which we're not working with anyway, but that is another type of graph that has asymptotes. It's not an e to the x graph. Again, another type of graph, but we're not dealing with them. It doesn't fit in any of those categories, so there are no asymptotes. And also, we can take a look at symmetry, and we can easily see that there's no symmetry. There's no symmetry because I only have part of a graph, right? Not part of, but I only have one side of the axes that I'm using. So if I were to take a look at trying to plot what I have so far, I think I've got the bigger grid. Yeah, good. I have nothing on the left-hand side of the graph. Well, if there's nothing on the left-hand side, I don't have any symmetry, right? All of my symmetries reflect either left to right or around the origin, which moves things from left to right or right to left. So there's no symmetries either. Okay, so we have an x value of 1/2 as our x-intercept. It's right here, so I'll plot that. Now we're ready for the calculus components, taking derivatives. So we're going to take the derivative of this radical function. All right, so what is the derivative of the square root of 2x minus 1? Mm-hmm. Mm-hmm. To the negative 1/2. Yeah. Is everybody good with that? We have a chain rule on this one. The 1/2 at the front and the 2 at the end cancel, so that's pretty nice. And the 1/2 that's a negative exponent is now going to dump it back into the denominator. So this is actually 1 over the square root of 2x minus 1. The top cannot equal 0. Agreed? Right? The bottom can. So the bottom equaling 0 gives us a place by which we have to be aware, right? And we know what that value is. We already found it. This happens at x equal 1/2. So on my sign chart, I only have one value, and it's not a very exciting one. And the reason is because the left-hand side of this is not in the domain. In other words, I can't test anything on the left-hand side. Anything I try is going to give me a negative underneath the radical. So I only have to do one test point. That's actually very nice. And I might as well just do the test point of 1 because I can, right? It's a nice one and it's over there. So if I put the number 1 into this function, 1 over the square root of 2 times 1 minus 1, do I get a positive or negative? Positive. So this means that the graph is increasing from 1/2 to infinity. It's not decreasing, and it has no relative extrema. So now let's do the second derivative. It's just as friendly in terms of the sign chart that we're going to get. So I really have, before I moved it back up, just this piece in the middle to take the derivative of, right? So now my negative 1/2 is going to come down. So I have negative 1/2. I have 2x minus 1. What's the new exponent? Would be negative 3/2. Yeah? And times the 2 for the inside function. The 2 here and the 2, not the negative part of the 2, but the 2 from the front we're going to cancel. So now I have a negative 1 over the square root of 2x minus 1 cubed in the denominator. So again, the top cannot equal 0. It's not possible. But the denominator could, and where would the denominator once again equal 0? Yeah, at x equal 1/2, right? The sign chart's the same sign chart that we did before. And so we're going to set up our sign chart with just a 1/2 in it. I can't test any points over here because they're not in the domain. I might as well test the number 1 because I can. So if I put the number 1 into the second derivative here, what happens? It's negative, right? The number 1 has to come out of this radical as a positive number, right? The square root's going to come out positive. So whatever is on the denominator is going to be positive, and I've got the negative on top. So it is negative, and the negative means that it's going to be what? Concave down. So my graph is concave down from 1/2 to infinity. So concave down and increasing. So increasing means I go uphill. Concave down means I'm going to curve so that it's pointing downwards-ish, right, as it turns. So this graph looks something like this. And there is no capacity, right? Like it doesn't have an asymptote that stops it. It will go up infinitely, just not fast, right? Not like a line or like a parabola graph going up or something like that. But it looks like this. It's not a very exciting graph to graph, looking for these features because it doesn't have a lot of the features, you know, changes and things and so forth. Any questions on that? Okay, so we have the web assign that's out there, and then you have the written work on this one as well.